Terraforming and settling Titan is often imagined as an attempt to force a frozen alien world into becoming a second Earth. But a scientifically grounded view suggests something far more realistic and far more interesting. Titan does not need to be reshaped into Earth to support human life. It already possesses several of the most difficult prerequisites for long-term habitation, and with intentional engineering, biological adaptation, and advances in space travel, humans could eventually thrive there in ways that are impossible on most other worlds. The journey itself is the first great hurdle. With the technology available today, reaching Titan is slow but entirely feasible. A human mission would rely on chemical rockets combined with gravity-assist trajectories through the inner and outer solar system, borrowing momentum from planets like Venus and Jupiter to reach Saturn efficiently. Using this proven method, the trip from Earth to Titan would take roughly 6 to 8 years one way, depending on planetary alignment. This is not a limitation of navigation, but of propulsion. The real challenge during such a long voyage would be human health. Prolonged exposure to microgravity, cosmic radiation, and psychological isolation. These problems are serious, but not unsolvable. Rotating spacecraft that generate artificial gravity could greatly reduce bone and muscle loss, while advanced closed-loop life support systems could recycle air, water, and waste for years at a time. Radiation exposure could be mitigated using water shielding, hydrogen-rich materials, and carefully designed spacecraft geometry. Travel times would improve dramatically as propulsion technology advances. Nuclear thermal propulsion, which uses a nuclear reactor to heat hydrogen propellant, could realistically cut the journey to 3 or 4 years while allowing much heavier spacecraft. Nuclear electric propulsion could further reduce fuel mass, trading speed for extreme efficiency. Looking further ahead, fusion-based propulsion offers the possibility of sustained high acceleration, potentially reducing travel times to less than 2 years. With such systems, Titan would no longer be a once-in-a-lifetime destination, but part of a regular interplanetary transport network. Faster travel does more than save time. It reduces radiation exposure, lowers life support demands, and makes sustained settlement possible rather than symbolic. Arrival at Titan reveals why it is so uniquely promising. Unlike Mars, Titan already has a thick atmosphere, with surface pressures higher than Earth's and a composition dominated by nitrogen. This means humans would not face explosive decompression or require heavy pressure suits just to step outside. The challenge is temperature and chemistry, not atmospheric absence. Titan's surface is brutally cold, averaging around -180 degrees Celsius, locking water into rock-hard ice while allowing methane and ethane to behave like rain, rivers, and seas. From a physical perspective, this cold is a form of stability. Titan does not bleed its atmosphere into space, and its thick haze provides natural radiation shielding that rivals or exceeds Earth's, protecting future inhabitants far better than Mars or the Moon. Beneath the frozen surface lies one of Titan's greatest assets, water. Titan's crust contains immense quantities of water ice, chemically identical to Earth's oceans, and evidence strongly suggests a global subsurface ocean of liquid water mixed with ammonia, kept warm by internal heat and antifreeze chemistry. This means oxygen, hydrogen, and drinking water are not scarce imports, but local resources. Oxygen could be produced industrially by splitting water ice through electrolysis, generating breathable air and hydrogen fuel at the same time. Over long periods, hydrogen could be vented or exported, slowly altering Titan's atmospheric balance in a controlled way. Energy, often assumed to be a weakness because of Titan's distance from the Sun, is in fact a major strength. Titan's methane seas represent one of the largest accessible chemical energy reservoirs in the solar system. Methane combustion, when paired with locally produced oxygen, releases large amounts of energy while producing water as a byproduct. Nuclear fission would complement this system perfectly, operating efficiently in Titan's cold environment and providing continuous, reliable power for cities, industry, and climate control. In the longer term, orbital solar collectors positioned above Saturn's rings could beam energy directly to Titan, bypassing atmospheric haze entirely. Titan would not be energy-starved, it would be energy-rich. Warming Titan does not require turning it into a warm, Earth-like planet. Human comfort depends on local conditions, not planetary averages. Even a modest increase in surface temperature would radically change Titan's chemistry, allowing stable liquid water environments beneath protective structures and within engineered basins. Highly effective greenhouse gases, far stronger than carbon dioxide, could trap infrared heat without destabilizing atmospheric pressure. Adjusting the optical properties of Titan's atmospheric haze to absorb more sunlight would further raise temperatures passively. Localized warming from reactors and subsurface heat extraction could create permanent temperate regions long before any global climate shift occurs. Breathable air on Titan would be manufactured rather than naturally evolved. Industrial oxygen production would precede biology, not follow it. Over time, synthetic organisms designed specifically for Titan's nitrogen-rich, low-light environment could assist by metabolizing hydrocarbons or ammonia and releasing oxygen slowly and predictably. These would not be transplanted Earth plants, but entirely new life forms engineered to function within Titan's unique chemistry. The result would be a stable, partially oxygenated atmosphere supplemented by localized enrichment, sufficient for human respiration without requiring full planetary transformation. Human biology would adapt alongside the environment. Titan's low gravity presents challenges, but it also allows architectural solutions that are impractical on Earth, including massive rotating habitats and lightly supported megastructures. Periodic artificial gravity exposure, medical intervention, and long-term adaptation could mitigate bone and muscle loss. Titan's dense atmosphere dramatically reduces radiation exposure, lowering long-term cancer risks compared to other deep space settlements. Over generations, humans could become physiologically optimized for Titan, not weakened by it. The most realistic path forward is not instant terraforming, but civilization-driven transformation. Enclosed cities would appear first, powered by local energy and built entirely from Titan's materials. These would expand into regionally warmed environments where partial exposure to the atmosphere becomes possible. Industrial systems would gradually replace uncontrolled methane seas with managed reservoirs, while oxygen levels rise slowly and predictably. Over centuries, Titan would become increasingly human-compatible, shaped as much by technology and culture as by chemistry and physics. Ethical considerations remain central. Titan's complex organic chemistry may resemble early prebiotic processes on Earth, and preserving large regions for scientific study would be essential. Terraforming Titan would need to be selective and cautious, respecting its value as both a future home and a scientific treasure. This is not about conquering a dead world, but partnering with a chemically active one. Titan is distant, but it is not unreachable. With current technology, humans could get there within a decade of travel. With near-future propulsion, that journey could be cut in half. With advanced nuclear or fusion systems, Titan becomes a regular destination rather than a remote frontier. Given enough time, patience, and scientific maturity, Titan could become humanity's most stable and enduring home beyond Earth, not by copying our planet, but by expanding what it means for a world to be truly habitable. If explorations like this spark your curiosity about space travel, planetary science, and humanity's future beyond Earth, please like, comment, and subscribe to the Science of This and That. Your support keeps deep science conversations alive, and your comments help shape what we explore next.